Electric field, part 0. In this video, we'll explain some interactions that happen from a distance, in particular the gravitational and electrical interactions. We'll start by the gravitational interactions. Newton has showed that all bodies, for example A and B, of masses ma and mb, will attract each other by a certain force. That is to say, the body A exerts on the body B a force of attraction such that body A attracts body B towards it. The force exerted by A on B is denoted Fa on B. This is the first attraction. Also, B exerts a force on A. B attracts A by a force exerted by B on A. By B on A. B on A. This is the second interaction. Hence, all bodies exert on one another a force of attraction. So what is this force due to? These forces are due to the masses of the bodies. These forces have opposite directions, that is to say, Fa on B equals to minus Fb on A. These forces have the same line of action. This is according to the principle of interaction, and they are directed in opposite directions. The magnitude of the first force, A on B, is equal to that of B on A. They are equal to G multiplied by the mass of A multiplied by the mass of B divided by the square of the distance between their centers if the bodies are punctual or homogeneous spheres. D is the distance between their centers. G is called the universal constant of gravitation. A universal constant of gravitation. It is always equal to 6.67 times 10 exponent minus 11 in the SI system of units. If the masses that we're studying are at a certain distance from one another, they exert on one another a force of attraction. It is an interaction that happens at a distance. It is a gravitational interaction that depends on the masses of the bodies that we're studying. This is a force that is due to the mass. The mass is responsible for such interaction. Let's take an application. If we have two persons, the first has a mass ma equals to 60 kilograms, and the other has a mass mb equals to 100 kilograms. Assume that their centers are separated by a distance of 2 meters. We're going to calculate the common magnitude of the force of interaction between these bodies. We have to determine the common magnitude of the force of attraction between these persons. This force is equal to G times ma times mb divided by the square of the distance. 6.67 times 10 exponent minus 11. This is a constant and it doesn't change. The mass of A is 60 kilograms, that of B is 100 kilograms. The distance d between them is equal to 2 meters. The masses are in kilograms. D is in meters. And the force is expressed in newtons in the International System of Units. The result is 1 times 10 exponent minus 7 newtons. The force between these two persons has an order of 10 exponent minus 7 newtons, which is a very, very small magnitude or is negligible. Then we don't mention this force at the person's level. We're going to calculate the force with which Earth attracts a person at its surface. Assume that the mass of this person is 80 kilograms and that Earth is a homogeneous sphere of mass 6 times 10 exponent 24 kilograms. The radius of Earth is 6,400 kilometers. Earth attracts the person according to the gravitational force of Newton like this. This is the force exerted by the Earth on the person. Now, what is the magnitude of this force equal to? The force exerted by Earth on the person is equal to G multiplied by the mass of Earth multiplied by the mass of the person divided by the square of the distance between the person and the Earth's center. The person compared to Earth is a particle. So this distance is no other than the radius of the Earth. No matter how tall the person is, his center will be at approximately 1.5 meters, 1.6 meters, etc. So this small distance from his center to the surface is insignificant compared to the radius of Earth. G is a constant no matter what, so we can calculate the magnitude of this force. G is 6.67 times 10 exponent minus 11. It's a universal constant, doesn't change. The mass of Earth is 6 times 10 exponent 24 kilograms. The mass of the person is 80 kilograms, all in the SI system. The distance between the center of Earth and the person is the radius, which is equal to 6,400 in kilometers. We have to convert it into meters. We multiply by 10 exponent 3. In this case, the answer is 781.6 newtons. This is the force exerted by Earth on the person. What does this force represent? This is the force of attraction exerted by Earth on the person, or simply it is the weight of the person. This is the weight of the person. The weight is given by the attraction force exerted by Earth on the person. The weight of the body, in this case the person, is equal to the mass of the person multiplied by the gravitational field strength. As a result, W equals to M times G. G is equal to W over M. G equals to 781.6 divided by the mass of the person, which is 80. The answer is equal to 9.77 newtons per kilogram. This is approximately 9.8, which is the gravitational field strength at the surface of the Earth. We have determined the value of G based on the magnitude of the terrestrial force of attraction written by Newton. Based on this formula, we have determined the gravitational field strength, which is 9.8 at Earth's surface. In conclusion, any body at the surface of the Earth is attracted by a force called the gravitational force of attraction. This force is due to the mass of the body. This force is always an attraction. This force depends on the mass of the body and the mass of the Earth, and it also depends on the distance between their centers. Let's now talk about the electrical interactions or Coulomb's interactions. We know that two charges of the same sign will repel each other, and two charges of opposite signs will attract. But what is the value of the force that exists between these charges? If we have two charged spherical punctual bodies, A and B, the charge of A in the first figure is opposite to that of B. In the other two cases, their charges have the same sign. Then they will repel. A and B will repel. In the first case, A attracts B by a force F exerted by body A on body B. A on B. B also attracts A by a force. This is the force exerted by B on A. B on A. This is the force created by B on A. So its point of application is A. For the other cases, A and B have the same signs, so A repels B. A exerts a force on B, so we draw it at B, and it has this direction. It's a repulsive force, so it has that direction. B also exerts a repulsive force on A, FB on A, that repels it away from it. So we draw it on A. Let's now give the expression of the force that exists between these charges. We know that FA on B equals to minus FB on A. FA on B and FB on A are forces of interaction that are due to the presence of the charges. These forces are opposite. What is the value of each force? We know that FA on B equals to FB on A as magnitude. They are equal to K multiplied by the absolute value of QA times QB over the square of the distance. We put an absolute value because the magnitude of the force can't be negative, and the charges can be either positive or negative. K is called Coulomb's constant. 9 times 10 exponent 9 in the SI system. QA is the charge of A expressed in coulombs in the SI, the same for B. D is the distance between the centers of the charges. This is Coulomb's law. Coulomb came up with this expression that gives the magnitude of the force of interaction that exists between two punctual charges. FA on B and FB on A are drawn on the line joining the centers of the charges. This is the formula that gives the magnitude of Coulomb's electrical interaction, which is called Coulomb's law. Let's calculate the magnitude of the electric force that exists between the nucleus and the electron in a hydrogen atom. In this hydrogen atom, the electron revolves around the nucleus in a circular motion of radius r equals 5.3 times 10 exponent minus 11 meters. The charge of the nucleus is given by, this is the charge of the nucleus, equals to plus E. E is the elementary charge, which is equal to 1.6 times 10 exponent minus 19 coulombs. The charge of the electron is equal to minus E, which is minus 1.6 times 10 exponent minus 19 coulombs. We want to determine the force by which the nucleus attracts this electron. This force is denoted F. The magnitude of this force is given by Coulomb as follows. K times the charge of the nucleus multiplied by the charge of the electron divided by the square of the distance between the nucleus and the electron. The charges are put in absolute value, by the way. The distance is all of the radius. The distance between the electron and the center of the nucleus is the radius of this trajectory. By replacing each term by its value, 9 times 10 exponent 9, multiplied by the absolute value of 1.6 times 10 exponent minus 19, multiplied by minus 1.6 times 10 exponent minus 19, over the radius squared, 5.3 times 10 exponent minus 11 squared. All these units are in SI. The magnitude of this force, 8.2 times 10 exponent minus 8 newtons. The nucleus attracts this electron towards it by a force F that is exerted by the nucleus on the electron. By the nucleus on the electron. This force, with which the nucleus attracts the electron, is responsible for keeping the electron in its trajectory.